First, we want to know, what is Boyle's law? First, we have two volumes to consider, the pressure and the volume. Here we see P is up, but V is down. So we say about these two volumes, these two values rather, they are inversely proportional. P is up and V is down. But what about Charles' law? Charles is another value. So P and V were inversely proportional. What about Charles' law? But what about volume and temperature? The volume and the temperature, what do they do together? We see 30 liters and 150 K go through 60 liters and 300 K. Both increase at the same time. T goes up and V goes up, both at the same time. They are directly proportional, both at the same time. So directly proportional. Charles' law describes a direct proportion, whereas Boyle's law described an indirect an indirect variant. This describes a direct variant here. Charles' law. How absolute zero was estimated here. Lusak's law, another law here. Pressure and temperature, what did those two do? 100 kilopascals, 300 K. What does that do? 200 kilopascals goes to 600 K. Both go up, we see. So another direct proportion, just like Charles' law. Lusak's law does the same thing. So T goes up, P goes up. Direct proportion. Here we see. (500 kilopascals), we see a burst. So Avogadro's hypothesis, all at P equals 1 atmosphere, T is equal to 25 centigrade, V is equal to 1 liter CO2, He, O2. What do we have here? At the same T and P, equal blank of some gas must contain equal blank. Equal volumes of gas must contain equal moles N particles. Avogadro's law, V and N. 1 mole of He, add gas, goes to 2 moles of He. Increase of moles equals an increase. Now, so far, we've seen that Boyle's law here, an indirect increase here in volume and pressure. So an increase in volume leads to the indirect increase in pressure. but an increase in volume leads to the increase in temperature, Charles' law. An increase in pressure leads to the increase in temperature, Lusak's law. And an increase in volume leads to the increase in moles, Avogadro's law. This is what we've seen with our chemical laws so far. Now, what does this all lead to? It leads to this giant chemical formula we see here. Right here we see PV over NT equals some number we're going to call R, which we're going to call a constant. All gases at some ratio. Now, we're going to call this ideal gas constant, R, which is equal to 0.08206 liters atmosphere over moles Kelvin. Yes, it's some giant ideal gas constant number we don't have the full abilities to put out entirely, but this isn't a math course, so let's have what we have here. So, the ideal gas law is what we have here, though. Pressure times volume is equal to the number of moles times R times T. The ideal gas law. You need to know for chemistry here. Pressure times volume is equal to number of moles times R times T. Ideal gas law. That's what you need to know. Alright, let's go see here. This is what's given on an exam. So, these two numbers. All this information, though, is given on an exam. You need to know it all, though. Do note it. Please do. Alright. No units of millimeters hydrogen, kilopascals, grams, or centigrade, though. Do note that, though. So PV equals nRT, though, is given on an exam. The PV equals nRT is given on an exam. The ideal gas constant is given on an exam. R, the constant, is important to note. Pressure, volume over number of moles, temperature, initial. What's initial and what's final. PV over NT1 is equal to some R, which is equal to some PV over NT2. There is some changes in P, V, T, and N as time goes on. Inversely proportional and directly proportional. P goes up and PV goes down. T goes up, V goes up, T goes up, and P goes up, and N goes up, and V goes up. So there is some important